Well, welcome to the May Structure Modeling Project video conference. Today we'll be talking about the concept of clustering. We'll be doing that in general and trying to identify areas where clustering is used in the scientific process and in the reasoning process and in the evaluation process. So it's kind of a high-level overview. The purpose of this particular report is to start developing this format of the scientific method of creating knowledge, what the different components are, and then we'll continue to refine that. But next, we really need to, after this one, we really need to do a paper on a utility value. And so then once we've outlined different kinds of value and value assessment, then I believe we'll have set the context to where we can go into these techniques a little more in detail. So anyway, clustering is used basically to help identify objects. And in the object identification and the when you're looking at things, you're making distinctions, then you want to say, oh, these things are the same, we'll kind of group them over here, group them into clusters and categories. And you do that by actually looking at variables or characteristics of the object. And that's a very fundamental way to start organizing the world and the perception. Another feature of this particular report is it focuses on Tryon work on who did cluster analysis, developed cluster analysis in the 1930s, and worked on it up until the 60s and 70s, and went all the way through actually starting doing calculations by hand or with a mechanical machine, and then dealing with computers and digital computers and the conversion of the methods to digital formats. Which is interesting because those really started introducing some fundamental issues between the human perception and the formal languages, which are really needed for the computer computation and the computer analysis. So we're going to go through and look at those, and also we briefly talk about Warfield's work a little bit, when he had a similar type of activity where he started doing most of his proof of concept work by hand, and that was translated over to computer programs. And that particular process also introduces some conflicts. And I'd like to just highlight the fact that I couldn't really get Warfield's printed code solutions to, not his code, but his solutions to work when I first started writing the programs. And then after I talked to him and found out that actually he was doing most of the work without a computer, and that he was using these different types of operators, then it became clear to me that how to approach a computer solution. But today, most everyone believes just right off the bat that these calculations and everything was done with a computer. And by having a digital computer, then what that does is that imposes some constraints fundamentally on the way things can be done. So I just think that is an interesting historical fact. So the primary scientific process, of course, is a fundamental set of steps which people agree to use to communicate about their views of the world and how things are developed and worked with. And again, this has been going on for a very long period of time. And again, I'm highlighting the fact here that within the last 100 years, digital computation has gained significance and prominence, and it's used, ubiquitously throughout scientific computing and scientific activities today. And one of the things about using computers and models and so forth is you can quickly overwhelm the human's capacity to deal with detail in using computers. So there needs to be some strategy or some mechanism that the human uses to deal with that large volume of data. And talk about a couple of them here. One is you can either use a computer-based system to reduce and create an alternate smaller set of symbols. And in the clustering information-based and object-based work that Mary and I do, that is one of the activities that we do. We actually reduce those, take a number of elements. If they fit a certain criteria, then we reduce them to one element, or one element. And that reduces the number. Warfield did a similar thing with condensation. And then, of course, there's other ways you can develop programs to sort, sift, search through data. But again, that's not really, it's giving you a smaller subset, but in some cases, it really doesn't help human perception and human learning. So we took the previous scientific process graph, which had the formal realm at the top and the natural realm, factual realm or nature at the bottom, and we inserted in the middle the human realm or perception. And really that's kind of the mediating layer between the factual realm nature and the formal model realm. And so what we're doing here is we're starting to make this a little more detailed and start looking at where specific processes are. This, again, is just a draft at that starting point, and we expect to develop it over a period of time. But essentially what it says is you have observations, and you compare that with historical data. If you don't have any historical data, you just follow through that and start to use abduction and induction to start create concepts. And then when you have multiple concepts you connect, and then you have a theory, and then you get your model theory. And then there's a number of ways that you can deal with the formal manipulation of the model theory. The previous chart only had deduction on it. Deduction usually gives you just one output, zero. I mean, maybe you have no solution, maybe, but if you do get a solution on deduction, usually it's just one. Fuzzy inference. Fuzzy inference, there's a couple of different methods, and so that will really give you a small number of outcomes, and you can evaluate those to decide which ones you want to accept or work with. The evolutionary computation is another formal manipulation process, which will give you a large number of answers or predictions. And then what you really need to do there is to select, using some criteria, to select a small set that the human evaluators can evaluate and select from further. It's a kind of a preliminary step in the selection process. It really doesn't give you a final answer. And of course, other formal analysis methods will give you an unlimited number of predictions, and there's many other models and logic methods, and so forth. But what we'll mostly focus on is this transition from the human perception, or creating concepts and transitioning to the formal method. So the statistics and clustering here is used to not only help identify and quantify your objects, but to make that decision of, okay, this is good enough for us to assume that it's true. So when you go from the value truth realm, value truth isn't necessarily true. And factual truth, bottom, isn't necessarily true. But when you go into the formal realm, the model realm, you have to make a decision and say, okay, we assume this is true. So it's like an axiomatic approach. So you say, okay, we now have enough data, enough information to say, yes, we can assume this is true, all this stuff in the formal realm, and then we will start our manipulations on it. Then we do select our manipulation, go through, you can do one of these, or you can do them in sequence, you can do them in parallel too. But when you come from the formal realm back into the human perception realm, again, we're transitioning from an area which is formally true into an area where it's not necessarily true. And I think one of the examples here, and I think Janet pointed out, was the idea that in some of the literature that people talked about events preceding themselves. Well, we really have no factual experience with that. In the human perception realm, we don't know about that. But you can model that in formal methods. You can model a system where events precede themselves. You can describe it, you can give axioms, in processes and so forth. But when you take that formal method, the output from that formal method, and you translate it back to the human perception realm, does it have any value? And so that's really what we're going to be looking at with this particular larger setup of process, is saying, okay, we want to be able to say, yes, we realize we can model almost anything formally, but what is the value of that formal realm formal manipulation once we bring it back into the human perception and the factual truth and value truth area? Let's say a model error and observation error. This approach can be formalized like a Kalman filter. In environmental restoration and environmental monitoring and so forth, there's formal ways where you will say, well, how good is my observation data set? How good is that? What's my observation error? And what's my model error? And using a Kalman filter, you can statistically describe very clearly what the combined errors are. And then if you need to have a better model and a better output, then you can make a decision, well, okay, I'm going to decide to expend resources and get better sensors and have better observations.
So we have a teleconference going on.
Or we can decide, well, we're going to spend resources and we're going to develop a better model. But in all those cases, it gives you a very clean way to make a value decision. Again, we're here in the value truth area. So what is their value decision on actually making a better model up here of the formal model world, or getting better instruments or better processes by which we can observe the factual realm or observe nature. So we'll start looking in more detail in these after we develop the value truth area in utility theory and just utility concepts a little bit more in our next report.
Can I ask a question at this stage?
Sure, go ahead.
What is the context here? Do you assume that every observer observes the same way?
No. And
okay,
so,
because
yeah.
isn't there something missing in the human realm, which is the confrontation of perceptions and the interpretation of the various perceptions that may differ?
Yes, that's absolutely true, and I think I basically touched on that a little bit now, and that's really a good point. And yeah, but the idea now is to say, I'm going to emphasize that this is a draft.
Yeah. Well, that's what we're looking at and discussing, but to me, it's almost like there's a straight line from observation to the formal model with some, assessment in between, but it may be more complex than that.
Right. So let's just take two different cases. Let's take the case where a single human being.
Yeah, the single human being is pretty straightforward.
Processes. And then the case number two is where you have 1,000 people performing this process.
Yeah.
And so what we're doing now is we're just starting to talk about the process, identify the areas, and then we will start talking about the variation of whether it's one person or 1,000 people.
Mm-hmm.
And further, this scientific method, mostly also, and especially in the value truth area, when we're talking about value, talk about the motivation. What motivates anyone to do this, right? And mostly scientists are motivated by their own personal, ability and need to explore things, and they just go and follow their instincts and their intuition, an individual doing that. And so that would kind of be closer to the scientific realm and closer to an individual scientist. But once we go back and look at this again, and we consider it now, we say, okay, well, what about a systems methodology, where we're looking to design a system of transportation or an economic system for a nation, where we have, thousands of people involved, and the motivation and value for that is not individual interest, right? Not individual intuition. There has to be a guiding value set that people within that 1,000 or 2,000 groups of people, they kind of use to guide them, right? So those are issues that we'll discuss later on, but you're right on. This is just starting. That make sense?
Yes, it does. What I just don't see here is whether, like, the meta-stabilization of different perspectives is done in this human realm then. So it's meant to be filtered and to achieve a unified position in order to create the formal model, right?
Well, yeah. So basically, what this chart is meant to convey is we have three realms: the factual realm, which is nature, human perception realm, and then the formal realm, right? And associated with these three realms, we have three kinds of truth: the model truth, the formal truth, the value truth, and the factual truth. And so, then what we have mapped on top of these three sectors is that are some basic operational and process steps. And so when people make a decision, right here, to go from the human realm, to translate from the human realm to the model realm, the key factor there is formal truth, okay? Because formal truth is required in the formal realm. It's not required in the value truth realm. So a key consideration there would be, well, who decides that it is good enough to go into the formal realm?
Yeah.
An individual scientist would make that decision themselves. I had 2,000 people working on designing a system for a nation. They would have to have a different type of truth and value set to make that decision among themselves. And then similarly, when you're going from the formal realm back to the human perception realm, and what you need to do here is you need to have, again, you say, well, who decides what's valuable here? Who decides what method I use? You have an individual scientist doing this, that individual scientist decides. You have a large group of people doing it, you need to have a different value set or decision-making process to do that. But we'll address that as we move along. So,
yeah, it's a key question, who decides the formal truth, but that's more of a philosophy question than, or political maybe also than anything else. So I'll leave this aside.
Yes, but I'm just trying to highlight the fact that that decision must be made for the transition to happen.
Yeah.
And most people don't highlight that. That's what you're doing here. You're making that transition, then you're going from, okay, this is kind of value truth to formal truth. And then when you come back, you say, okay, now I have formal truth. How does that match my reality? How does that match my value system? And one of the pattern things we're looking at here, of course, is the augmented model exchange isomorphism, which we can use to identify patterns. The abstract relation type, which we can use to actually formally encode the data that's coming back in. Once it's formally encoded, then what you can do is you can make value distinctions on that. Okay.
So I just came in late here, so I'm not quite following what's going on.
Okay, Janet, how you doing?
Good, good.
All right.
Is there debate within formal truth, or is it only the interpretation of what you derived within the formal, where the decisions come in, where the question is who decides what the interpretation is?
Yeah, so basically, in this particular chart right here, we have the top, we have formal truth, and then we have a transition line from formal truth to value truth. And it's crossing that transition line. So going from value truth to formal truth, and then from formal truth back to value truth. Who makes those decisions on that evaluation? If it is in the current context, the proper thing to do, the transition from value truth to formal truth. And then the next is who makes a decision which says, okay, we have some calculated or some derived formal truth, then who decides that that matches correctly with value truth? So
right. So I would assume that any time there is multiplicity of perspectives, you're in the value realm, so that it's I think that in the formal realm itself there wouldn't be any debate, but as you're saying, the crossing, to the extent that you have to leave the value realm, you have to have some agreement or agreement on or responsibility for the encoding choices. That's all I'm saying is I think everything about debates, choices, responsibility, multiplicity of perspectives would be within the value truth realm, is my view. And that it's leaving that or coming back into it that has that value truth character that is debatable. Whereas formal truth is is not debatable because it's all relative to formal, conditions. Does that make sense?
It does, and I think that's the kind of the heart of what I'm driving at here. But there's something there's something a little bit also kind of underlying, and that is the fact that anything with a digital computer has to be modeled formally, and that's another theme here. It's like saying, okay, when we are using these computational processes, then we have to cast them into this form of manipulation. And so the question is, one, what you put into that formal manipulation, and then once the formal manipulation is complete, what do you do with the output? Is it valuable, right? So, and I think that the example I gave before you came on was the idea that where the people had in the process what precedes, they made a very nice formal model that events precede themselves. And as you pointed out, I believe it was you said, yes, you can do that. That's a formal model. There are your actions. You can have a world where that happens. And you need to make a decision that, does that have any value in the real world? Do people have experience with that? Can we use that? And those are the types of things that we can now start assigning, places that we can at least discuss them using a map like this.
So, but this is an open system, right? It's not where we're in a closed organization where everybody has the same purpose. Here we have conflicting purposes, or not necessarily.
Oh yes, you can have conflicting value systems, right?
Okay, because something that we're starting to discuss in as far as general systems theory and isomorphy are concerned is that it's been ages that system scientists have been trying to come up with the general systems principles. So probably following this type of process or
that's what that is.
model.
Right.
And without success, because there never is an agreement or an authority to decide on what becomes the formal truth. So if you look at and that's a suggestion that some, including me, are having, and that's been operationalized in other domains, and which is related to clustering actually, is to say that you don't actually in a intentional way get to an agreement, but you meta-stabilize points of view because you generate clusters of perspectives, and that there's a kind of meta perspective that emerges from it. I don't know if it makes sense.
Well, yeah,
but that's an option that I just wanted to mention, but I don't want to derail the conversation with crazy ideas.
Okay, so let's talk about general systems theory in this chart, right? And so we did the general systems theory discussion a few months ago. But what it said was general systems theory lies somewhere between the formal systems of mathematics. So all the formal systems of mathematics up here, they are not in general systems. And so, and the specialized theory, right? Specialized theory of specialized, sciences, chemistry, physics, and so forth. So somewhere between them is general systems theory, but general systems theory can use mathematics, so the mathematics is used in the mathematical realm. It's also used in the general systems realm, and it's also used in the specialty systems realm. So mathematics is everywhere. So from a formal language standpoint and general systems, then all three categories have formal language. The difference is, in my opinion, is that the informal contextual information that goes between the specialty theories, the specialty sciences that are used in general systems theory. So general systems theory mathematics and the informal concepts in general systems apply to almost all specialty sciences. And then in the specialty sciences, you have mathematics, the general systems components, and then their added secret sauce that makes them a specialty science. And so I believe that this type of chart is going to help us look at those mechanisms and map that out. Anyway, that was the plan for it. So yeah, I don't think it's crazy. I think it just needs to be articulated and as we're moving forward. So hopefully that made some sense. All right.
Yes.
So the arrangement and relationship of objects and actions and process steps in Figure 1 are preliminary. So I want to emphasize that. We're just going to be starting with it. General schema is a starting point to start developing this in a little more detail. And some of the areas where it needs to be developed is, do you have a single person doing this? Do you have 2,000 people doing this? What is the goals? What's the value system? How do you rate and rank them? But to be specifically about clustering, though, and use of formal techniques, and I really want to talk about space-based and object-based clustering. And so when you have objects, you're going to look at their characteristics, and you're going to figure out how they're the same and how they're different. And you're going to group them according to the categories, according to their characteristics.
So to be clear, it's similarities on a certain number of criteria or variables. It's not as a whole. It's not A is similar to...
You have an object, right? You have an object.
Sorry?
I say if you, given an object, any object?
Yeah, given any object, is it just that object A and object B are similar, so they clustered together, or can they be clustered together on this variable or criterion and not on that one, and similar to something else on other criterion?
Right.
I mean, you put them in boxes. Do you create categories with boxes, or do you create a graph?
Well, the dimensions, right? Here, basically, when we're talking about spaces, the variables are the dimensions of the space. And so you can basically do that when you're mapping them out and you're looking at the variables. First of all, you have to select which ones are important. Then you map the dimensions and so forth. But those common characteristics, a key difference between object-based and space-based is that object-based clusters appear to be mostly used when you're using the system in a discovery mode. I'm going to go discover systems and objects that are already here, right? So your space-based clustering usually focuses on the design mode. So, okay, I'm in the process of designing some system. I'm going to use space-based clustering to help me determine what I should design or what types of things I should design. And going back to the book here from Tryon, he did O analysis and V analysis. He wrote his first book on this in the 1930s, basically as a set of desk instructions, because he and his wife were both psychologists. And in those days, the psychologist, the researcher had to produce and you know, calculate all their own data, do their own data analysis by hand. And so his wife, the story goes that Tryon got tired of doing not only his data analysis, but his wife's data analysis. So the first book that he wrote is basically a desk instruction for his wife on how, so she could calculate the data herself and he wouldn't have to do it. But again, what you have here is an expert, a subject matter expert that designed the experiments, done the observations, collected the data, is now processing the data to create clusters, okay? And he started before digital computers, and he developed this all the way through the time when digital computers came online. And one of the fellows that worked with him, a quote from the book is that as Tryon saw it, the price of such mathematical elegance is one's not knowing exactly what one had measured. And for the sake of psychological understanding, he decided to obtain cluster scores by straightforward addition, even though they were not correlated with, even though they were then correlated with one another. And so here you have a scenario where a person is rejecting, an expert is rejecting a mathematical formal technique that everybody uses all the time because it really doesn't provide any use or value or insight. And also rejecting it because he was doing the calculations by hand, and to do anything different was like about 10 times more work. And it didn't really add anything to the value of the outcome. And then when they had digital computers come around, they basically did all the calculation for you almost instantly. He decided not to use that, is my understanding anyway, because it didn't add any value. Even though you can do computations very cheaply, you want to do computations that add value and insight. Okay. So then the idea here, of course, was to minimize the cognitive and manual labor and calculation. And what they point out in the book was basically they had tremendous issues with taking their approaches and their natural language way of working with things and then getting that across to the computer programmers and the computer operators. It's created a whole different set of issues. Okay. Of course, they point out Warfield performed all of his initial proof of concept calculations regarding clustering techniques manually, and then he even added Boolean operators to reduce the manual labor with that. And so the idea here is that people that are experts in the area are developing their own formal techniques to achieve their own value goals, reduce calculation, labor, reduce complexity, and so forth. Okay, so the cluster development. So again, I think the main thing we want to say here is, go back to the chart, is that O analysis and V analysis is here on the left-hand side in human perception realm. We have historical data. You're manipulating that data, you're clustering it, you're looking at it, putting it in a form that gives you more information, which then hopefully triggers human abduction or induction. You create or modify your current concept set, make a decision then that goes, okay, that can go into the formal realm, look into model theory, and then basically do the manipulations and bring them back. And then the other place for clustering is over here in the predictions area. You can collapse or expand types of clusters on graphics, on matrices, on different network types. And you can, when you do that, you can either change your abstraction levels, or you can be looking at different values. It's kind of vague, but I don't, just want to point out that you can do that, and basically it can be used as a cognitive and computational complexity reduction approach, right up in the prediction area. And there's a number of those that we have outlined before in our previous reports. Okay, so let's see, common characteristics, space-based. So the object and variable analysis, just two basic types of statistical data analysis. And one of the things I found very interesting about Trion's work was that when they were selecting characteristics about the objects of interest, that he would not allow them to select an object that didn't, or a variable that you couldn't use to place the objects in the strict order. So not only did he minimize manual calculations, he also used the strict order so he could use the logic involved with the strict order to again reduce the amount of calculations required. So thought that was a very interesting aspect of his work. So you use these techniques to generate objective values, needing to place any specific object in its proper position in a strict order. Selection of strict ordering relationship requires a process other than object analysis or variable analysis. And that's the selection of the strict ordering relationship. That is key to the subject matter expert that knows what's going on. That's not a mechanical calculation. So you need to, it's fundamental and it's very important, and it's not a mechanical calculation process. So dimensional cluster analysis is basically the way that it's used in the system design world. Is you start creating a dimensional space, and that dimensional space, and dimensions are usually characteristics of the final system or some attribute to the final system. You can take those, populate them that way, and then you do these dimensional processes to create evaluation structures. And really, you can do this in a way that you're creating systems concepts, systems goals, systems structures, and then you can interrelate those. And one of the things that Warfield did along this line was what he called the quads. And the quads fundamentally supported a kind of a small process where you had a bunch of, let's say, alternatives. You select among those alternatives, and then you take those selected alternatives, you cluster those together in a dimensional space, and then you evaluate the clusters to see if they achieve a goal. And it's kind of a 3 or 4 step process. The key part of what Warfield put together on that was the fact that, well, you can weave these little quads into tapestries so that the goal of any one quad can feed into an alternative in another quad. So I can have a quad that has 15 alternatives, and then each one of those 15 alternatives has been selected in quads below that. So you can, it's kind of a way to make an object or a process and a selection object, the quad, that you can weave together or put together in different configurations. It's a pretty powerful analytical tool. Okay, So anyway, so the cluster analysis has many forms and applications. We're just starting to talk about the topology, where they would go, what it would look like. There are two primary approaches. Object-based cluster development is fundamentally different from space-based. One is really kind of a system discovery. The other one's kind of a system design. And yeah, so that the space-based subdimensions. So here, the final little figure here kind of shows the object-based cluster, where you identify and analyze the objects. They're there. The key part of this is in the discoveries, you're going out and you're going to discover these things that are already there. Space-based clustering, basically, in design mode is, well, what you want is not already there. You're going to have to design it. And so you determine the cluster dimensions, and so you identify the objects in the object-based cluster, then you determine the cluster dimensions, then you analyze the object clusters to find out whatever characteristics or features you're interested in. And a space-based cluster basically just says, well, you know, what's the main objectives? What are the main space? What's my dimensions of interest in the system that I'm going to design? And then you identify subdimensions of interest. The subdimensions need to relate, of course, to the primary dimension. And then you populate and enumerate the objects in the subspace. And at the end of that process, you actually have clusters in both cases, but getting to these clusters is completely different. And I believe it's important to make this distinction. And then once you've made this distinction about what you're using the clusters for, then you can start categorizing the different clustering techniques and when and how it should be used. So we have about 13 minutes left. What would people like to talk about?
Let's see. I have three devices in my lap: a MacBook, an iPad, and an iPhone, and I hope I'm not getting feedback between them. This is very interesting, and I'm sorry I missed, Joe, you and Helene were talking about the relationship between these three types of truth and general systems theory. So I missed that. I would.
Let's see. Let's go back and
hear. Yeah.
Right here. And so, so we did the definition of general systems theory. That's lies somewhere between the formal theories of mathematics, right, which is the formal language of all theory, right? So general systems is not in this area, and the specialized theories of the specialized sciences, right? So in the formal truth, basically, the only thing that you have up here is mathematics. In the value truth, you can have factual truth, formal truth, and value truth, all three in here. You can use them same way. And down here in factual truth, of course, you have the processes by which you determine factual truth. But the idea is that formal truth or mathematics can be used in all three areas, so it's everywhere. So what's the difference between general systems theory and specialty systems theory? Because general systems theory components are also available in specialty systems. What makes specialty systems different is whatever their secret sauce is that makes them a specialty science, right? There's some difference from the general systems component. So in the specialty system science, what you have available is formal systems general systems and specialty systems. In the general systems area, you just have formal systems theory and general systems theory. You don't have available there the specialty system. That makes sense? That was
and I'm sorry, you're using specialty system as
so this
special
is
system?
basically a technical report 19.
Right.
And let's see, it's clears.
Do you have a graphic from that we could look at?
Well, yeah, why don't I do that? Why don't I just go ahead and see if I can find that real quick and pull it up.
Yeah, this is all very helpful, and I think it's converging in a good way. As you said, articulating these differences is key, because, for example, when people don't understand the three types of truth, then they jump to conclusions in one or the other and then end up arguing.
Really?
Yeah.
Yes.
Yeah, really.
People argue. I can't believe that. I don't know. Yeah, so it's there are problems. So there's no doubt about that. So just wait a minute. I got to stop this screen share, and then I'm going to have to come up with this other one over here, and this application window. Okay. Okay, this is the general systems theory development out of Technical Report 19.
You make it a little bigger.
What's that?
That's better. Thank you.
Yeah. Does everyone see that?
Yeah.
Okay. So that just says, okay, mathematics, right? It just has formal mathematical theory. That's it. And of course, in this one, we talked about the object language and the meta language. Now, for those people who are following SOA's work, right, on ontology, we talk about what he's talking about now is you have a formal type of ontological language that then depths into informal pools of semantics everywhere. And when Moorfield mapped the idea that the object language for systems is mathematics, and that the meta language for systems is natural language, that's, in my mind, identical, same thing, right? That SOA's talking about now in his ontology. So it's just a sideline there when talking about the object languages and the meta language. So there it is. Got about 7 minutes left.
Right. So, so specialized. Is it? Where am I? Specialized disciplines. Okay.
Yep.
Yeah. Which would be other people talk about special or specific and specialized. We're not making hard and fast distinctions at this point between those words.
Right.
So it's like you're iterating in the specialized disciplines that you have both the formal. I'm wondering about how do you put the the three-way value split, or I'm sorry, the three-way truth split. How do you put that into this picture as well?
Well, so mathematics just has formal truth, period, right?
Right.
And so the general systems theory can have formal truth, and it can have informal and value truth, right?
Right.
And factual truth. And specialized disciplines can have formal, value, and factual. And so really this chart, what it says to me is the most interesting part there's no formal way to tell the difference between a specialized discipline in theory and a general systems theory. It has to be done. It has to be done informally.
Right. Right. And then also that what you just said about the three kinds of truth are necessarily, wouldn't they necessarily be involved in the general systems and specialized systems?
Yeah, both. Yeah, they're all three types in general systems and all three types in specialized.
Right. 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 Or I guess you have a choice about how you present it. Either the formal mathematical theory for general systems is supplemented by value language and natural language, or in the next box down, right? Either you're pulling the formal in from the formal mathematical theory, or all three are, well, you are saying informal there.
Yeah, so the formal has no informal. So mathematics has no informal.
Right.
And so really what you need to do, using this chart, the key thing is saying, okay, you just need to figure out what's the informal difference between general systems theory and specialized systems theory. In many cases, that might just be a lexicon or a taxonomy, or because they are just carving out a piece of the world. So maybe it's just these set of tags, that you're assigned to objects in that part of the world.
So the under interpretive structural modeling in the right column, the informal general systems descriptions, those are where you go back from the formal, the BSM, into the human realm,
exactly.
Right. Yeah. So these diagrams are starting to be possible to map them together.
Yeah, that's the hope. That's the hope. So that basically what happens here is, like in general systems theory, the factual truth, the factual nature realm is unlimited. In the specialty systems realm, the factual realm is limited.
Why? What? So I don't understand that. Why is that different?
Well, you have specialty systems, right? As specialty systems, they limit themselves to certain kinds of nature.
Oh,
right?
Okay.
But general
So
systems,
they're limiting themselves. Okay, I see. Yeah. Okay.
Right. That's how you specialize, by limiting. But general systems theory can apply to them all, to everywhere. So it's unlimited.
Right.
Okay. So we're down to about the last 2 minutes. So let's see, who's up for 2 weeks from now? Which is going to be May 19th.
I'm not sure yet.
Okay, so does anybody want to present anything 2 weeks from now?
Yeah, I can continue with the structured democratic dialogue playbook and get more into the diagrammatic aspects as Janet was suggesting.
Excellent. All right, we'll put you down for the 19th, Kevin. All right, is there anything else people would like to discuss before we...
I want to know, Kevin, did you deliberately want to look like the Pioneer plaque human saying hello to the aliens, or or it's a little bit on the live long and prosper, but
it's nice.
Yeah, that was a picture of me facilitating a healthcare futures event, and so he caught me mid explanation about something apparently.
Mhm.
Ah.
You're our ambassador.
So
Yeah.
any other pressing questions?
No, it's yeah, interesting elaboration here.
All right. So I think what we'll do is we'll then have Kevin will be continuing on the 19th, and I will send out a notice. Take care. Have fun.
Thank you.